All right, so today we're looking at theoretical probability, and our learning goal is to identify the differences between theoretical probability and experimental probability. So yesterday, we learned that experimental probability is the number of outcomes an event occurs over the total number of trials. So with experimental, we know that we have to conduct some type of experiment, and we actually have to participate in these trials in order to collect data. With theoretical probability, we are basing all of our assumptions off of reasoning. And what this means is that we do not conduct an experiment. There are no trials. This is all based off of what we would assume to be true or what we would assume would happen. So we do this through the formula P, which means probability, and then in parentheses we put the event that we're looking at. So what specifically are we wanting to happen? That goes inside the parentheses. And then we have the number of favorable outcomes over the number of possible outcomes. So this would be like our total, while our favorable would be what makes that event true. And so we are going to take a look at a cube. And so when you have a cube, there are 6 sides, and we want to know the probability of rolling a 0. So we have 6 sides to this cube, and this isn't like any type of cube. We have 2 zeros, and then 1, 2, 3, and 4. And so up here it looks like there's 2 cubes, but really it's just 2 different visuals of the same cube. And so first we need to figure out, well, how many total numbers do we have? So we know that there are 6 sides to a cube, but if you didn't, you can count the possible outcomes that we would have. So there are 6. So this would be the number of possible outcomes. And so if I'm writing this as a fraction, I'm going to have 6 as my denominator. Then I need to figure out, well, how many would make this true? So I want it to roll a 0. So I know that I could roll this 0, or I could roll this 0. So since there are 2 zeros on this cube, we have 2 favorable outcomes. So those are like our 2 possibilities. We always need to simplify our fraction, so we're going to divide by 2 on top and bottom. And so this will give us our final answer, which means that the probability of rolling a 0 would be 1/3 of the time. So we would assume before conducting any experiment, just looking at this dice or this cube, we would just assume that we would roll a 0 1/3 of the time because there's 6 sides to the die and we have 2 zeros on them. So we would assume that it would be 1/3 of the time. So now we're going to take a look at the spinner. And this spinner, you will notice there's 8 sections, and each section is equally divided. That's important because with theoretical probability, every section has to have an equal likelihood of being chosen. So I can't have one section that's larger than the other. Now I need to find the probability. So we notice that there are 8 possible outcomes, which means that would be my denominator. And I want to know, well, what is the probability of it just landing on a red one? So I'm going to look and see how many reds do I have. I have 3 red. So then I would assume that my theoretical probability would be that I would land on a red 3 times out of the 8 total outcomes. So let's try the next one. Red with an odd number. So again, we're going to look at those red, but I only want an odd number because I need this to be true, both parts. So this one's no longer an option and this one's no longer an option. Those are both even. So I only have one odd number that's red. So I have one that would make it true out of the 8 total sections on the spinner. And so 1/8 of the time, I would assume that I would land on a red odd number. So then with green, there are 2 greens, and that's all that I need to make it true. Just has to be green. We see that there are 2. So 2 out of my 8 spins, but we know that this can actually be simplified down to 1/4. And so we would assume that 1/4 of the time I would land on a green. So I want you to do the next 3 by yourself. So now we have a bag full of buttons. And these buttons are different colors, and they also have different number of holes in them. I don't know if you've ever noticed that on buttons, but this one has 4, while over here these have 2. And so that's going to play a role in what we're looking at today. So I want to know the probability of choosing a blue button. Well, before I can do that, I need to figure out my total possible outcomes. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 buttons. Each have an equal likelihood of being chosen. And how many are blue? I see that there are 6. So when I simplify this down, I get 1/2. So then my theoretical probability would be that half the time I would pick out a blue button. What is the probability of choosing a button that has 2 holes? I know on your notes it's going to be a little harder for you to see, so I'll zoom in for you guys. So we see that we have 1, 2, 3, 4 buttons that have only the 2 holes in them. The other ones all have 4. So again, I didn't add or take away any of the buttons. I still only have 12. Only this time there's 4 that makes that statement true. There are only 4 buttons that have 2 holes. When I simplify this down, I divide by 4 on top and bottom, and I get 1/3. So 1/3 of the time, I would assume that I would get a button that only has 2 holes in them. So your answer should be C. Right away, we can tell that it's not B and it's not D because we got 1/2. And then honestly, looking at this side, we didn't have 8 buttons, we had 12. So you also could have gotten rid of that one. Just some test taking skills. All right, so now we're going to look at this spinner. So this is a spinner, and you'll see that there's one really large red section and one really small blue section. The thing is, we cannot find theoretical probability unless all sections of the spinner are equal. And right now, we have one giant section that's red and one small that's blue, and so those aren't equal. The good news is we can actually cut this spinner and fix it so they all have equal sections. So now I just turned it into fourths. So now, yes, red has more likelihood of being chosen because there's a lot more that's red, but at least the sections on the spinner are all the same side and the same size. And that's what's really important here. The reason that it's important is because had we not drawn these lines here, we would think that, okay, the probability of spinning a red would be 1 out of my 2 times, which would be 50% of the time. And that's not true because I have a lot more red on that spinner. Once I actually break it apart into equal sections, I can see that I would land on red 3 out of the 4 times, which is more of a 75% chance. So the likelihood of landing on red increased because the sizes of my spinner had to be the same. And this one makes more sense. So now let's look at what's the difference between theoretical and experimental. Theoretical is based all off of reasoning. So we're not conducting any trials. We compare the number of favorable outcomes to the number of possible outcomes. While experimental is based off of observations and trials. And so we compare the total number of times that this actually occurred, and then we take that and divide that by our total number of trials. So if we're looking at, will a baby be a boy or girl? First, we need to decide the total number of outcomes. So we have 1, 2 outcomes, boy or girl. So that's going to be my denominator. And I want to know the probability of it being a boy. Well, I have one out of the two possibilities. So that's 50% of the time it should be a boy. Experimental is then actually collecting real data and actually conducting these experiments to figure out how many babies were born that were boys and how many were born that were girls, totaling them up, and then actually finding the probability of our boys, which is the number of boys, over the number, our total number. And when we divide those two really large numbers, we see that we actually get, it's not this, that shouldn't be there. We actually get 51%, which is really close to our theoretical, and that should actually happen. So the more trials and the bigger your total is, the closer it should be to your theoretical. All right, so now we're going to look at our examples. So we're trying to decide, is it an experimental probability or a theoretical probability? So a soccer player took 12 shots on goal and scored once. So this one is experimental. And the reason experimental is because this player actually went out and took these 12 shots and he only scored one time, or she. So because they actually took these shots on net, we know that it had to have been an experiment. So I want you to try B and C on your own. And we're going to move on to simulations. So this is when we try to recreate what would be a real world situation. And so it's just a way to model it without actually having to go and conduct these experiments with a bunch of people. And so you can use objects such as coins, number, cubes, spinners, all to simulate the probability of a situation occurring. And you assign each outcome to either the coin, one side of the coin, or a number on a cube, or a part of the spinner to simulate what you would think would happen in real life. So for a situation, if there are two outcomes, then a lot of people might say, okay, we'll toss a coin. That's a way to simulate how to actually determine these outcomes. So I know that I've used this to make decisions on where I would want to go to eat for dinner. So do you want Panda Express or do you want Taco Bell? So if you flip a coin, you assign each side an outcome. And then when you toss that coin, that's my simulation of making the decision. So it's not actually you having to do it. So 6 equal outcomes, you could roll a cube. 8 equally likely outcomes, use a spinner. So in class, I use a spinner to pick people to come to the board. So instead of me actually having to conduct that experiment and actually have to pick somebody, it simulates it for me. So it's simulating my decision making. So we are going to look at a class that has the same number of boys as girls, and each day a teacher chooses one student at random to take attendance. 180 days. So how many times would you expect the teacher to choose a boy to take the attendance? Well, since there's two options, boys and girls, and they each have the same number as boys as girls, we would assume that each would have an equal chance to take the attendance. And so since there's two possibilities, or two possible outcomes, we're going to take the 180 days and we're going to divide it by our possible outcomes, and we get 90. So we would assume that 90 days a boy would be taking attendance and 90 days a girl would be taking attendance. So this is our theoretical probability. Our experimental would be conducting an experiment, but we aren't going to do that over 180 days. So to simulate 180 days, I would flip a coin 180 times. And I chose a coin because there's an equal chance of heads as tails, and just like there is as boys of girls. And so you can simulate this by flipping a coin a bunch of times and collecting that data and then seeing how close is it to our theoretical probability.